Okay, the force diagram. We'll go back to our original framework that we looked at when we were calculating reactions. And at this stage we've drawn a space diagram to scale, and we've applied Bose notation to it. So we've lettered the spaces between the forces, A, B, C, D, E, F, and we're now ready to draw our vector diagram. Now the beauty of the Bose notation is that it links the vectors. Because each force has a common letter, each adjacent force has a common letter in its identification, this means that the head of this force, the head of the vector of this force, is going to be the tail of the vector of this force. The head of this force is going to be the tail of the vector of that force. So we can just simply, we'll start at an unknown. Now I've assumed that we haven't bothered to calculate the reaction at the hinge when we calculate the reactions. We can leave that on because it's only one unknown, and so that's going to fall out when we draw the vector diagram because it's going to close a polygon, as we'll see shortly. Okay, so we've just put the reaction at the hinge just simply there. We don't know what angle it is, so once again I'll draw a big question mark beside that to show that we know it's there, but we don't know what angle it's acting at. We don't know what its magnitude is. Okay, so we'll draw the force diagram for this. We'll start at the unknown because that means it's going to be the last one we try and put on, and so it will be already on the diagram. So we'll start with A, and we'll start with a point over here at, and we'll call it A. A convention is that when you go from the space diagram to the force diagram, you go from uppercase to lowercase. And this simply stops any confusion between the two diagrams. So we start at A, and to get to B, we've got to go down a distance of 10 kilonewtons. And the scale I'm using is 4 kilonewtons per 4 millimeters per kilonewton. Okay, so we just simply come down 40 millimeters to B. And that's our vector AB. Its direction is A to B, it's downwards. A is the tail, B is the head, and its magnitude represents 10 kilonewtons. Next force we'll put on is the 20 kilonewton force, and this is going to be known as BC. Its tail is going to be B, which is already on the diagram, and its head is going to be C, and it's going to be 80 millimeters long, representing the 40 kilonewtons. And it is simply in the direction of that force. Put on BC, CD, we've got to come down a further 10 kilonewtons. Okay, so CD is simply down another kilonewtons to D, and you can see on here that we've already got DA representing our hinge, our unknown force. We've got it on here, D to A, so it's a line up there joining D to A. The direction of that reaction force at the hinge is from D to A. From D to A, so we go D to A. Okay, so it's in the direction that we actually drew it. Okay, let's look at putting some of these other members on. It's a good idea to go around the outside first because one of the letters is already going to be on the diagram because these are representing the external forces, so they are already on the diagram. So AE is going to be on a line parallel to the space diagram, and it's going to be somewhere on the line there. If we now put on BF, then that's going to be somewhere on a line going through B, and F there. Okay, CF, parallel line going through C. You can see here we've got F is somewhere on that line, F is somewhere on that line, so it's actually going to be here. So that's going to be our point F. which means that BF has no load in it. It has no magnitude. It's the same point. So BF is what we know as a redundant member. We could take that member out and the framework would still be stable. Let's just keep going here. We put on CF. Okay, DE. DE is going to go through D and B there. That's pretty obvious that that's going to be point D. Okay, so now we can put on EF because we've got E already on there. So we just simply take a line parallel. We take a line parallel to EF and we drop it down to go through F and through E, and there it is. Okay, it's already actually on the. So we've taken that line and drawn it parallel on the diagram. Okay, the magnitude of the forces is simply the length of the line. So the magnitude of the force in this member here is simply Fe. Okay, so you simply measure its length, which I'll do roughly. It's 90 millimeters. Okay, so you just use that for the scale, and that will give you the magnitude of that. So that's going to be the magnitude of that line there. And it equal 90 over 4 kilonewtons. Okay, the next module will deal with how we test whether these members are in tension or compression. Okay, so that is the essence of drawing the force diagram. Doesn't matter how complex the structure is, the vectors are always parallel to the members in the space diagram, and the magnitude of the force is given by the length of that vector. Okay, thank you.